Welcome back, I'm that chemist, and today we have another episode in the Toxic series, and we're actually kind of doing a follow-up on the last episode about steroids. If you haven't seen that video, I'll put a card to it here and you should go check it out. So the same author of that paper is present as an author in this paper, Figueroa. Now, Figueroa has been a bit of a meme in the Discord for a week or so, and essentially, the thing about Figueroa is he's got a first authorship on over 150 papers, which if you know anything about publishing, that's insane, especially in the modern day. Because most of the time, if you're the first author on a manuscript, that means that you were the researcher involved with doing the experiments firsthand, okay? So I'm not even sure why there's so many authors on this paper, given the extremely small amount of work that's reported, but nonetheless, here they are. So it's kind of odd that Figueroa has this like massive background of first authorship. You might have also seen I did a community poll post where somebody had showed me an email saying that, oh, they've been reported for academic misconduct, for data falsification or fabrication. But as far as I can tell on Retraction Watch, there aren't any articles that have been retracted from him. And because he has so many, I think we need to at least show a few more papers where we see this acetonitrile magic, okay? So let's start. There are several studies for the synthesis of oxycycle derivatives using some reagents, which require special conditions, have been reported. The aim of this study was to synthesize two Oxycan derivatives from either imidazole or 2-methyl-imidazole. Now this is important because they don't actually use imidazole. The chemical structure was evaluated through both 1H-NMR and 13C-NMR spectroscopic analysis. The results showed a moderate yielding from Oxycan derivatives. Okay, what you see in the NMR and 13C NMR wouldn't tell you what the yield was like, so that's not really a super interesting thing here. Also, he uses this phrase Oxycan, which is technically like a term you can use. If you type that into ChemDraw and you do convert name to structure, you'll get an 8-membered ring with 1 oxygen. But if you Google search Oxycan, literally this paper comes up. So this is not a common motif. It should be mentioned that reagents used in this investigation are not expensive and do not require special conditions for handling. Now, what you consider special conditions to be is a little bit arbitrary, and it's a little bit weird to include this in an abstract, but nonetheless, they decided to include it. I just want to highlight here that this is from Wiley, from the Journal of Heterocyclic Chemistry. Now, if you're not familiar with Wiley, Wiley is really well known as the journal that hosts several high-impact journals, such as Engavanta Chemie. And Engavanta Chemie is a very well-known journal, especially in chemistry. And so the fact that they're happy to have another journal, Journal of Heterocyclic Chemistry, publishing garbage like this, really makes Wiley look terrible. So if you're from Wiley, maybe you should get your people to start evaluating this sort of thing a little bit more. But nonetheless, let's continue. So I'm just going to kind of go through here and point out some of the concerning stuff in this paper. For several years, there has been a great interest in the development of heterocyclic compounds in the chemical and pharmaceutical industry. That's fair. It's a little bit vague, and so anyway, we'll continue. In this way, several oxycycle derivatives have been prepared using different strategies. In what way? In this way. It says in this way, but it's not clear what way they're talking about. Like, yeah, there's an interest, but that doesn't tell you how you're making stuff. And even if there's an oxygen in the heterocycles, you know, that's fine. There's a lot of other things in heterocycles. And so here they basically say there's a bunch of different ways to make oxygen-containing heterocycles with different conditions. Fair enough. Then they have one concerning statement here that says, furthermore, other data showed the synthesis of 2-fluoro-5-oxypene derivative from a bicyclic epoxy alcohol analog using DAST as a catalyst. And so the issue here is DAST is not a catalyst. I am not familiar with any instance where DAST can be used catalytically, and in this case you can see you're converting an alcohol to a fluoride, which is nucleophilic fluorination, and usually this is done with an excess of DAST. So it's not a catalyst, kind of a bad lit review. But we can just kind of gloss over that and continue. All these data showed the preparation of several oxycycle derivatives using some protocols. That's just saying several different oxygen-containing heterocycles can be prepared, smiley face. It's like, that adds no value. However, these methods use different reagents that may require special conditions, such as high temperatures and differences in pH, which can produce low yields in some reactions. This is super vague and not helpful. Like, obviously different reactions are going to have different conditions, and different compounds are going to require slightly different nuanced conditions to work better or worse. That's just life. That's chemistry. Okay, and once again, I want to highlight that they say that they can either use imidazole or 2-methyl-imidazole, except here they didn't even spell it right. It says 2-methyl-imidazole, so that's kind of not great either. The editor should definitely have done some editing for this paper. There are several reports on the preparation of oxocyclic derivatives which require special conditions, such as high temperatures and differences in pH, which can produce low yields in some reactions. Now, I wouldn't call those special conditions, I would just call those conditions. Analyzing these data, in this investigation, 2 Oxycan derivatives were synthesized using a series of reactions as follows. So analyzing these data in this investigation, it's just like it's unclear. Maybe this is an ESL thing, but it's very unclear what they're trying to say here. But like if I was writing a paper, what I would write here is based on the complex conditions that have been previously reported in the synthesis of heterocycles, we decided it would be advantageous to develop a new set of conditions which were more amicable to methodologies adopted by most chemists, which might just be like a rhetoric thing, but nonetheless. So there are several studies using some reagents. Throughout his papers, you see this a lot, some reagents, some conditions, some papers. And so here's this imidazole, which is not imidazole. So this is dihydroimidazole. And normally if you see a ring like this, you can tell that it wants to be aromatic, and it's missing a double bond to be aromatic. Now they do some magic chemistry here, okay? So they add acetonitrile once again, but they add it to this sp3 carbon using catalytic copper. No explanation of mechanism. They might have meant to have a double bond there, but they definitely do not have a double bond there. Okay, so even if they had a double bond, a 2+2 cycloaddition between an already aromatic system and acetonitrile is bonkers, especially at room temperature. Even with copper as a catalyst, you know, it's ridiculous. And so here they're just basically saying that they could do that in both of these cases. Okay, so I'm going to go through the NMR a little bit, but like if you look at the NMR spectra, they're obviously fake spectra. Now, they usually have the correct number of peaks approximately where you might see them, but they don't have legitimate NMR spectra. They also have a supplementary information section which has many of the same spectra, in addition to some other ones like carbon NMRs, but they're just completely bogus. They also have some weird nomenclature. So here you see 2,3-dihydroazete fragment. Normally, if we were talking about fragments, you'd only be looking for fragments in like a mass spec, but because they're talking about NMR, it's a little bit weird to call it a fragment. Or you might say like portion of the molecule. They also have some interesting introductions here. Besides, the mass spectrum from 2 showed a molecular ion. A methyl-linked fragment, a little bit weird. Now, another thing that's kind of weird is they call them bicyclo-3,2,0 heptadiene derivatives, which would be right if they were carbon derivatives, but they should have called it a triaza bicyclo-3,2,0 heptadiene derivative, because, you know, if you gave me a bottle of, if you said you gave me a bottle of heptadiene, bicycloheptadiene, and then there's 3 nitrogens in it, it's like, well, you didn't tell me there's any nitrogens, so you lied. Now, they show the same thing where they have mass spec data for their different compounds. They don't have any like original mass spectra. You can see that these NMR spectra are just totally bogus. You can see that there's lines underneath the peaks. They're so low resolution that there's absolutely no way you could see anything ever. So that's not great either. But we can just continue. Here they talk about some protocols, and they say that in this investigation, either compound 2 or 4 reacted with 5-hexyne-1-ol in an alkaline medium to form 5 or 6. And so the concerning thing here is they say there are some protocols for hydroamination, but really boutique special conditions are required. Why? Because these aren't easy to make. Usually making cyclic ether derivatives, especially for large ring sizes, isn't a trivial ordeal, which is why these obscure ferrocene derivatives, some nickel derivatives, in this case, it's done with just dichloromethane. Man, if you could do cyclizations with just dichloromethane, you should be doing that already, right? Lanthanide chemistry, rhodium chemistry, or zirconium. Now, I can guarantee you, if you could do chemistry with, like, sodium hydroxide, no one's going to use rhodium in a million years. Like, why would you bother using rhodium if you could do chemistry with dichloromethane, okay? It's also worth noting that they say the NMR spectrum showed several signals, and they have their 13C NMR spectra, and here we can see the mass spectrum for 4, showed a molecular ion of 207.13. Now, if you build this in ChemDraw or if you just calculate the molecular weight on your own, this is the wrong mass. Presumably this 207 is actually meant for compound 5, but unfortunately they just made a mistake here. The biggest mistake, of course, was publishing this. So you can see here's another quote-unquote proton NMR spectrum where you can see a line underneath the peaks. You can also see that these are just fake peaks, really, really, really low resolution. They also say that they do this in CDCl3, but there's no CDCl3 peak, so that's another thing that's somewhat concerning. Okay, so they let us know that there are several chemical strategies for the preparation of oxycycles using some reagents. So there's several strategies using some reagents, and this doesn't add anything to their discussion because they're not talking about methods that they use. They're just talking about more literature review, which should have been part of the introduction. Okay, so they said in this investigation, 2 Oxycan derivatives were prepared using a previously method reported. And so this previously method reported is using iron trichloride for a PRIN cyclization, but they don't say that that's what they're doing here. And to be honest, the mechanism that they're using is a little bit bogus. And so what they do is they take their alcohol that they add onto this nitrogen using sodium hydroxide, which I just kind of glossed over. Let's just go back up for a second here. So essentially what they're saying they can do is just in the presence of sodium hydroxide with an alkyne, they will add in the nitrogen to the terminal position of the alkyne, which is also not the type of addition you'd expect to see, because that would be anti-Markovnikov, and these are Markovnikov conditions. Even that being said, it would be more challenging to add a nitrogen to an alkyne like this than the authors lead you to believe. Like, this is not a trivial transformation. Why did just one add? How come this didn't randomly re-aromatize? Like, this is also a weird motif. We're not even talking about how crazy this bicyclic system is. It's just totally bonkers. Okay, so now they say they take cinnamaldehyde, and in the presence of ferric chloride, they get this product. They don't show you a great mechanistic explanation. They say, as is evident by the stabilizing effects, they say this is why they get an 8-membered ring and not a 7-membered ring. Now, I think both of these would be allowable, but I haven't fully analyzed whether or not they would follow the ring cyclization rules. And you can see here that, again, we have some more crazy mechanisms where we have a ketone that just becomes an alkoxide. The alkoxide starts as like a central atom that's going hashed into the page. This is kind of like the abducting a cow stuff that we saw in the steroid episode last time. And then here you can see that once they have their alkoxide coordinated to the iron, now it's not negatively charged. It's got a net positive charge all of a sudden. Okay, so that's kind of special. Okay, the alcohol attacks the positive charge. You have a shift of electrons. That's not too bad. They don't really tell you where and how everything happens, but nonetheless, it does what it does. They then have a cyclization, which is a little bit interesting. So what happens here is they show the more substituted position attacking the carbocation, and then the alpha position generates a positive charge. However, if either of these were to form a carbocation, it would definitely be on the more substituted position, and you'd have a rearrangement through the shift of an R group or of a proton if that was going to occur. They then show that this chloride is able to attack, and then that forms this product, and then they just rotate it to show you the other way. Now, the biggest issue here is not only do they have an alkene, they have an enamine. So if we go back up here, you can see that they have an enamine. So if they did a reaction with an enamine, you always will have nucleophilic reactivity in the alpha position, never on the ipso carbon. And so the fact that they're saying the ipso carbon reacts is also just contradictory to like what's known about chemistry. And so your typical reaction of an enamine is shown here, where you have an electrophile and you get an iminium as your product. So you can also see that in their product, they don't have an iminium, just they suddenly magically reduce that system. They still haven't oxidized their non-aromatic system to an aromatic system. They also have the wrong geometry for this alkene here. There's just a lot of issues, okay? So we got some more crappy NMR spectra, some other interesting ways to digress between sentences, and let's just kind of look at the NMR spectra again. So they say imidazole. We already figured out earlier that imidazole was actually not what they used. They used dihydroimidazole, but fortunately the reactions were stirred to room temperature. So they don't tell us what temperature they were at originally, but after stirring, they eventually reached room temperature. They stirred them to room temperature. They also said something interesting here. Following the product, was purified via crystallization using methanol water. Okay, that's fine. Now, the thing that's not fine is they say they use CDCl3D. Okay, it's deuterated chloroform. I'm not familiar with deuterated chloroform, but if you've used deuterated chloroform before, you can let me know down below. The same problem as the last paper, something that really hurts, is that their carbon NMR has the same number of megahertz, but in their case, it isn't mega, it just megahertz. So there you go, 300 hertz. So they have this issue in all of their spectra. They say they give melting points and whatnot, IR, etc. I'm not even going to address any of those concerns because the data that they give is just blatantly falsified. Okay, here we have some more stirring to room temperature, and then they say that they remove a solvent. So let's look at this experiment. In a round bottom flask, 10 milliliters, it's a 10 milliliter round bottom flask, either compounds 5 or 6, cinnamaldehyde, and ferric chloride anhydrous were stirred to room temperature at 72 hours. And then the solvent was evaporated. What solvent? Where's the solvent? Okay, but they do a very interesting crystallization using the methanol hexane agua system. Now, if you know anything about agua or methanol, they don't mix with hexane very well. Okay, so this is another really terrible paper. Let's just look at the conclusions and we can wrap this up. In this study, a facile method for the preparation of two Oxycan derivatives, 7 and 8, from either imidazole or 2-methylimidazole were prepared using some chemical strategies as reported. On the other hand, it is noteworthy that the chemical structure of these compounds could be relevant to produce different effects in some biological models. Now, I consider myself a biological model, and I can definitely tell you there is some different effects being produced in me right now. They have some extra spectra of carbon NMRs that look just as bad as their proton NMRs at the end of the paper. And if you're interested, you can go and look at that online. So I'm quite disappointed with Wiley for letting this get published. I'm disappointed that the editing quality of this isn't even good. And I don't know how it's possible that this guy managed to get 150 papers like this out. If you're able to do this and get 150 just total BS papers out, and there's no like blacklisting of your name for even trying to submit an article like this, it's extremely concerning, especially for the university that this guy is from. So if you like this video and you want to see more Super Figueroa papers in the future, I'd be happy to do more videos. It would really help out the channel if you left a like and subscribe, and I hope you have a great day.